Welcome. So the topic we'll be discussing in this lecture is knowledge engineering in FOM. So basically we'll be discussing an example. We'll be taking an example and for that example, how can we build the entire knowledge base using first order logic? That's what we are going to discuss in this session. So what is knowledge engineering? So knowledge engineering is the process of constructing the knowledge base. So when you take any problem or if you want to solve any problem using artificial intelligence, first the knowledge of that particular domain, we have to capture the knowledge of that particular domain, and the domain knowledge should be incorporated in the system. So this process of constructing the knowledge base is called as knowledge engineering, and this knowledge engineering will be done by a knowledge engineer, and the job of the knowledge engineer is to investigate the domain. First, he should study the domain, he should learn the concepts of the domain, and he should create a formal representation of the objects and the relationship of the object within the domain. So this is the role of a knowledge engineer. So this knowledge representation is a very key aspect. Only if the knowledge is captured in a proper way and in an accurate way, then only the inference will be proper. If the knowledge is not captured in a proper way, then it will have an impact on the inference. Okay. So this knowledge engineering process, basically, it includes these 7 steps. The first is identify the task. That is what we want to do. What is the purpose of our knowledge base? See, we may be talking about a particular domain, but in that domain also, what is the task? With what task in the mind we are interested in that particular domain? So we expect the AI system to answer what type of questions or what type of queries will be raised and what is expected. So that is what is called as identifying the task. Then assemble the relevant knowledge. So this is just studying the relevant knowledge. Identify the relevant knowledge. We are not representing. This is not a step of representing. This is to collect the relevant information of the knowledge. After collecting the relevant information, then decide upon the vocabulary of predicates, functions, and constants. Then depending on the identified knowledge, we have to decide the vocabulary of the knowledge base, like which should be used as predicates, which should be used as functions, and what are the constants, all those things. After doing all these things, then we have to encode the general knowledge about the domain. So general knowledge means what? General knowledge means something like a rule, which is not specific to a particular case, but which is generic. But which is generic. So, for example, if you take in Olympus World, the uh, the room adjacent to the pits were breezy. That is a general info, right? But a particular room, say the particular floor 2,2,2 contains pit. That is a specific information. So here, this step 4, it talks about only general knowledge. Whatever the general knowledge, that should be encoded into the knowledge base. Then the 5th step is encode a description of the specific problem instance. Here we provide specific details about the problem. In case of Umpus World, if you see, there is a pit in 3,1. So that is specific to that particular problem. And Umpus is in a particular cell 1,3. So these are specific info related to that particular problem. So that is what the 5th step. The 5th step is to provide details about the specific details of the domain or the problem which we are talking about. And the 6th step is pose queries. So actually with these 5 steps, the knowledge base construction was done. But now we have to check whether the knowledge base is constructed in a proper way or not. So to check that, we have to pose the queries. Pose queries to the inference procedure and get the answer. And check whether the system is providing or responding in a proper way or not. If the system is not responding in a proper way, then then the mistake is, then somewhere we have missed some details of the knowledge representation. So if the system is not responding in the expected way, then there is something wrong with the way in which the knowledge is represented. Then we have to debug that, and we have to solve that. So that's what the last step, debug the knowledge base, right? So actually, when we initially provide the knowledge, we cannot expect the knowledge base to respond correctly for everything. Surely at some places it may behave in an unexpected way. So we have to repeatedly do these steps several times, and then only we can assure that the knowledge base is error free. Okay, fine. Let us discuss the knowledge engineering concept with this example. So basically this is an electronic circuit. So it's very self-explanatory. There are two XOR gates. This is an XOR gate, this is an XOR gate, and two AND gates. This is an AND gate, this is an AND gate, and one OR gate. And actually this it contains three inputs. So this circuit we are calling it as C1. This entire circuit is called as C1. And this circuit C1, it contains three inputs, 1, 2, and 3. And it contains two outputs. These are the two outputs. The first two inputs goes to X1. Okay. And the third input and the output from X1 goes to A2. Third input and the output from X1 goes to A2. The output of A2 and the output of X1 goes to X2. Okay. And the output of X2 is one of the output of A2 goes as the first input of O1, and before that the first two input were also inputs for this AND gate A1. And for this OR gate there are two inputs. The first input is the output of A2, and the second input is the output of A1, and this output is the second output of the circuit. Okay, so this we want to represent using an first order logic, right? So this as a whole, the entire circuit, it has three inputs and it has two outputs, right? So let us see how it works. So first we have to identify the task. What is our task? Our task is to represent this circuit. So that is what our task. Okay. Second is assemble the relevant knowledge. So what are the relevant knowledge here? So here relevant knowledge is, we should know like what is XOR gate, how XOR gate works, what is AND gate, how AND gate works, what is OR gate, how OR gate works. This information we should collect, right? And what is so if you one is here and the same one is taken here, it means that the same signal is passing here. Then if this is one, this will be also one. If this is zero, this will be also zero. So identifying or studying this and understanding this, that is what is the second step. Assemble the relevant knowledge. The third step is encode the general knowledge of the domain. So here, what are the general knowledge? So actually this requires a lot of thinking. So we have identified these as the general knowledge. This is one of the general knowledge. It says that if two terminals are connected, then they have the same signal. So what does it mean? If two terminals were connected, then they have the same signal. We can say that this is one terminal. This is one terminal and this is one terminal. Actually, these two terminals were connected. If they are connected, then they'll have the same signal. So if this is one, then this line also will be one. If this is zero, then this line also will be zero. Right? Similarly, this terminal and this terminal, they are connected. So they should have both same signal. If this is one, this should be one. If this is zero, this should be zero. So this is a generic information which we want to code. So how could we represent that using first order logic? So that can be represented something like this. For all T1, T2, T1 represents, T1 is a terminal and T2 is a terminal and connected of T1, T2, T1, T2. That is, if T1 is a terminal and T2 is a terminal and T1 is connected with T2, it implies that signal of T1 is equal to signal of T2. That is, whatever the signal in T1 will be same as that of the signal in T2. So this is a generic info we are pushing to the knowledge base. Similarly, the next is, this is another generic knowledge we are adding to the domain. The signal at every terminal is either 1 or 0. So this is basically, it is a logic gates. So it will take either 1 or 0 as input, nothing else. So either all these three inputs can be 1, or all the three can be 0, or any combination of 0 and 1s. So at any line, if you take, it will be either 1 or 0. So how do we represent that? For all t, terminal of t, so any terminal if you take, it will have some signal, and that signal will be equal to either 1 or it will be equal to 0. So if you take any terminal, that terminal basically it represents a signal, and that signal will be either 1 or 0. Okay, fine. And the third is, connection is commutative. Connection is commutative in the sense, if you say that, say let us assume that this line, we'll call it as T1, terminal 1. Let us call this line as terminal 2. Now these two lines are connected. So here connection, here it means that we can say that either T1 is connected with T2, T1 is connected to T2, or we can say that T2 is connected with T1. Either way we can say. So both are same. So how do we represent that? For all T1 comma T2, connected of T1 comma T2 is bidirectionally equivalent to connected of T2 comma T1. If T1 is connected to T2, it also means that T2 is connected to T1 and vice versa. Right? Then there are 4 types of gates. So basically, in our circuit, there are what are the gates? We have XOR and an OR, but we are also including NOT. NOT also we will consider. So with NOT, there are 4 types of gate. So how do we represent that? So that is represented something like this. For all G, gate of G, so if something is a gate, and K, and if K is the input for the gate, and if K is the input for the gate, then type of the gate implies K. Then depending on the type of the gate, the what will be the K is the whatever the input, no, the same thing you will get as the output. For example, for an AND gate, if you give only one input, the same output you will get. For an OR gate also, if you give only one output, you'll get the same output, right? So that's what it says. So the so mm, so the gate can be either AND gate or OR gate or XOR gate or not. So these are the 4 possible gates. So the gate can be either AND gate or OR gate or XOR or not gate. And next we are going to represent the details about the AND gate. What is meant by an AND gate? So in AND gate, the output will be 0 only if one of the input is 0. So this is how we can define an AND gate. An AND gate is a gate whose output will be 0 if at least one of the input is 0. So for all gate of G and type of gate. So here type represents what type of gate it is. Okay. Here type represents what type of gate it is. If type of gate is equal to AND, right? If type of gate is equal to AND, then it implies that the output of the first output, there is only one output for the AND gate. Okay, whatever we are discussing here, there is only one output. So here this one represents the first output. The first output of this particular gate, its signal will be, the signal of the first output will be 0. Will be 0 under which condition? There is a condition bidirectionally equivalent to there exists an n such that signal of input, this is input, at least one of the input is, so this n represents all the input to the gate. Okay, so there exists an n such that signal of input of n comma g equal to 0. So there are many inputs to the gate, but one of the input, if one of the input is 0, then the output will also be 0. That's what here we are representing, right? Similarly, if you take OR gate, an OR gate is a gate whose output is 1 only if any of its input is 1. So OR gate is 1 whose output is 1 only if any of its input is 1. So it is similar to that for all gate of G, and the type of gate will be OR. If type of gate is OR, it implies that its output here 1 represents its first output. There is only one output. Output of 1 comma G, that signal, the signal of that output will be 1. It means bidirectional it is equivalent to saying that there exists an n such that its input, the n comma G, its signal, at least one of its input is 1. At least if one of the input is 1 for an OR gate, then the output will be 1. At least if the one of the input is 0 for an AND gate, the output will be 0. That's what this rule says. Then XOR gate. So if you consider XOR gate, the XOR's output is 1 if and only if its inputs are different. So this is the rule for XOR gate. Its output will be 1 only if its inputs were different, right? So for all G, gate of G and type of G, G represents gate. For all G, G is a gate, and if type of G is equal to XOR, it implies that the first output of the gate, its signal is 1, is bidirectionally equivalent to saying that. So we are considering XOR with only 2 inputs. Okay. So one of its both these inputs should be different. So signal of the first input to the gate, its signal should not be equal to the second input of the gate signal. In that case, if the first input is not equal to the second input, then the output of this gate will be 1. Okay. So this is how we represent XOR gate. Then NOT gate. So NOT gate's output is different from its input. So its output will be just an reverse of the input. So for all G, gate of G, and type of G is equal to NOT gate, it implies that its first output, the first output of the gate, its signal, will not be equal to its input. Okay, the first output of this gate will not be equal to the first input of the same gate. So that is how we derive the NOT gate. And then the gates except NOT gate have 2 inputs and 1 output. So all other gates. So basically we have discussed the 3 gates: AND gate, OR gate, XOR gate, and one more gate we have discussed is NOT gate. Apart from NOT gate, all other gates they have 2 inputs and one output. Okay. Apart from AND gate, apart from NOT gate, all other gates have apart from NOT gate, all other gates they have 2 inputs and 1 output. Okay, so that is represented like this. For all G, gate of G and type of G equal to NOT. If the type of the gate is NOT, if the type of the gate is a NOT gate, okay, then it implies that arity G comma 1 comma 1. See, this arity represents basically this arity is a term which we are using to represent the circuit. Arity is a term which we are using to represent the circuit. So it means that our circuit, if it is a NOT gate, then that part of the circuit contains a gate with 1 input and 1 output. Okay. So that's what it says. So the circuit contains 1 input and 1 output, right? So this is only for the case of NOT gate. For all G, gate of G, and K equal to type of G, okay, and K equal to, for all G, gate of G, and K equal to type of G, and K equal to AND, or K equal to OR, or K equal to XOR, arity implies arity G comma 2 comma 1, right? If it is some other gate, if it is I mean only if it is NOT gate, then that gate will have 1 input and 1 output. If it is not a NOT gate, if type of gate is not NOT gate, so this is here only we are talking about gate. Here this is K is something else, we are not bothered about that. Okay, if this K represents this K represents basically type of the gate. This K represents basically the type of the gate. Okay, and K, it is equal to type of G, and K can be what? K can be either AND gate. I mean, the type can be either AND or XOR. If the type is AND or XOR, then the circuit, then that then the circuit for those gates will have two inputs and one output. So that's what this statement says. Okay, next. A circuit has terminals up to its input and output arity and nothing beyond its arity. So here arity represents like what is the maximum input and maximum output. For example, when you say that arity of C comma I comma J, which means that C is a circuit. This circuit, uh, we are not talking about the entire circuit. Okay, sometimes it may refer to entire circuit, or it may also refer to a specific gate. So uh, so it depends, right? So arity of C comma I comma J means C represents some circuit, and this circuit can have maximum I input and J output. That's what it says, right? And this rule, what it says, a circuit has terminals up to its input and output arity and nothing beyond its arity, right? A circuit will have terminals maximum that is given by its input arity and output arity, not beyond that. So how will we represent that? For all C comma I comma J, so for all C comma I comma J, C is the circuit, Ij is the number of inputs, I is the number of input, J is the number of output. Circuit of say C and arity of C comma I comma J, that is the circuit C has I input and J output. It implies that for all n less than or equal to I, for all n less than or equal to I, terminal of input of C comma n, right? Input of C comma n, and so this is for all n. This is for all n, but as long as the n is less than or equal to I, because I represents what? Maximum input. Okay, as long as n is less than or equal to I, so the circuit can have maximum that many input, and it will not have any terminal which is greater than I. N greater than I, for n greater than I, the input of C comma n is nothing. Okay, so basically it means that maximum it can have this many inputs, not beyond that. Similarly, and for all n less than or equal to J, terminal of output. So output, how many outputs we can have? We can have n output, but the condition is the value of n should be less than or equal to J. So that many output we can have, and n greater than J, for n greater than J, output of C comma n will be nothing, right? So basically this says that the number of inputs and outputs uh, were controlled to a specific extent. Gates, terminals, signals, gate types, and nothing, all are distinct. So somehow we should tell the knowledge base that these things are different from each other. Gates, terminals, signals, gate types, nothing, all these are distinct from each other. So for all G comma T, gate of G and terminal of T implies G represents gate, G is not equal to T represents terminal, which is not equal to 1, which is not equal to 0, which is not equal to R, which is not equal to AND, which is not equal to XOR, which is not equal to NOT, which is this is not 6, which is not equal to nothing. So by this, we are informing the knowledge base that all these are different things, right? And then we are saying that gates are circuits. So one is the overall circuit, but individual gates are also circuit. So for all G, gate of G implies circuit of G. Okay. So far what we have done is we have represented the generic knowledge of the domain. We have represented the generic knowledge of the domain. Okay. So that's what we have done here. Now let us encode the specific problem instance. So for the given problem, whatever the circuit we want to represent, for this problem, for this circuit, there will be some specific information. Let us encode that knowledge now. So what we are going to do? So first, we are saying at the top level, we are saying that circuit of C1 and arity of C1, 3, 2. What does it mean? So here by this we mean that we are going to represent this entire circuit. This entire circuit is called a C1. This entire circuit is called a C1. And C1 contains how many inputs and how many outputs? C1 contains 3 inputs and 2 outputs. So that we are saying that we are representing like this circuit of C1. The C1 is a circuit, and C1, that is arity of that is C1 contains 3 inputs and 2 outputs. So this is one specific information about the circuit which we want to represent. Okay, right. And now our circuit, it contains how many? It contains 2 XOR gate, 2 AND gate, and 1 OR gate. So this info also we should represent. So that we are representing like this: gate of X1. X1 is a gate. So here if you see, X1 is a gate, and what it is type? Its type is XOR. So we are saying that gate of X1 and type of X1 is XOR, right? Similarly, we can represent other things also. Gate of X2, gate of X2 and type of X2 is equal to XOR, right? Similarly, A1 and A2, gate of A1 and type of A1 is AND, and similarly A2, gate of A2 and type of A2 is AND. So this is a specific knowledge to this particular problem. And gate of O1 and type of O1 is equal to OR. So that also we are representing. So gate of X2 and type of X2 XOR, gate of A1 and type of A1 and gate of A2 and type of A2 and gate of O1 and type of O1 OR. So now at the top level, we have specified the circuit, we have specified the individual gates. Apart from this, we have to also specify the connectivities. So this also comes under encoding the specific problem instance. So how the connectivity goes, right? So if you see here, the first input of, so C1 contains 3 inputs, 1, 2, and 3. We can say this is the first input of C1, this is the second input of C1, this is the third input of C1. And we can say that this is the first output of C1 and this is the second output of C1. Okay. So what we say here, the first input of C1 goes as the first input of X1, and the second input of C1 goes as the second input of X1, right? Okay. First input of C1 goes as the first input of X1. So that how we are representing here. Let us see. So what we are saying here, connected of, see this statement, connected of input of 1 comma C1, which means that first input of C1 is nothing but the first input of X1. So first input of C1 is connected to the first input of X1, right? That's what this statement says. Okay, connected of in of 1 comma C1 comma in of 1 comma X1. So why we are doing like this? I guess you are following. The first input of C1, this is C1, this is C2, this is C3. Okay, so first input of C1 is nothing but the first input of X1. So we are saying that in of that is in of 1 comma C1, right? In of 1 comma, this is C1. In of 1 comma C1 is nothing but in of 1 comma X1. This is, and whole bracket, it is connected. That is, the first input of C1 is connected to the first input of X1. Similarly, how will we represent this? The second input of C1, in of 2 comma C1, the second input of C1 is connected to the second input of X1, right? So this is connected. Second input of C1 is connected to the second input of X1, right? Similarly, this C1 and C2 goes to A1 also. So that also we can represent in of the first input of C1 is connected with the first input of A1, right? Connected. Similarly, the second input of C1 is connected to the second input of A1, right? So now we have specified these connections, 1, 2, and all these things, right? Like that, we can we can we can build up the knowledge base. So that's what this says. So connected of the first input of C1 is nothing but the first input of X1. Okay. First input of C1 is also the first input of A1. Second input of C1 is nothing but the second input of X1. Second input of C1 is also the second input of A1, right? Okay. Third input of C1. So let us see where is third input of C1. Third input of C1, where it goes. So if you see here, third input of C1, it goes to first input of A2 and second input of X2. So how will we represent that? Third input of C1 is connected to the second input of X2. Second input of X2. So this is connected. Similarly, third input of C1, third input of C1 is connected to the first input of A2. It is connected with the first input of A2. Okay, right? So that is what this next two rule says. Third input of C1 is connected to the second input of X2, and third input of C1 is connected to the first input of A2. Right? Now, if you see the other inputs, they also depend on the output. The first input to X2 is nothing but the first output of X1. There is only one output, but we call it as first output of X1. So here we use the term out. First output of X1 is connected to the first input of X2. So this is also connected, right? So you can observe there will be a rule something like this. First output of X1 is nothing but the first input of X2. First output of X1 is nothing but the first input of X2. So on and so forth, we frame all the rules. Next, the first output of X1 also goes to A2. So if you see here, the first output of X1 also goes as the second input of A2. So that is like what? The first output of X2 is nothing but the second input of A2. So this is connected, right? Okay. Then what else? So this A1 part we already finished. Then this output of A2, the first output of guest A2 goes as the first input of O1. So first output of A1, first output of A1 is nothing but the first input of O1. So this is connected. This is connected. Okay. Then what? This first output of A1. So this is A2. First output of A2 is the first input of O1. And the first output of A1, first output of A1 is the second input of O1. Is the second input of O1. Okay. So this is also connected, right? Okay. Then the first output of X2 is the output of C1. First output of X2 is nothing but the output of the whole circuit. And the first output of O2, O1 is nothing but the output of second output of C1. So how can we say that? First output of X2 is connected with the first output of C1. So for the whole circuit, this is the first output also, right? So this is connected. Similarly, you can say that the first output of O1. The first output of O1 is nothing but the second output of C1, right? So like this, we frame the rules. Okay. So that's what it says. First output of A2 is connected with the first output of O1. First output of A1 is connected with the second output of O1. First output of X2 is nothing but the first output of C1. And first output of O1 is nothing but the second output of C1. So this is nothing but encoding the specific knowledge, right? So now after encoding this generic knowledge and specific knowledge, now we can query the knowledge base to check whether the knowledge base is responding properly or not. So for example, we can ask the knowledge base query like, what combination of inputs would cause the first output of C1 to be 0? For which combination of the input, the first output will be 0 and the second output will be 1. Okay, so the query says that there are 3 inputs, right? So the 3 inputs can take any values between 0, 0, 1 and 1, 1, 1, right? Okay, so basically it can take 8 possible inputs. So for all these 8 possible inputs, for which possible input the output will be in such a way that the first output will be 0 and the second output is 1. If you want to ask such a query to the knowledge base, then that query can be represented in first order logic, something like this. There exists I1, I2, I3. Input 1, input 2, input 3. Such a way that the first input to C1 is equal to I1, and the second input to C1 is the whole circuit, is I2, and the third input to C1 is I3. Okay, and the first output of C1 is 0 and the second output of C1 is 0, 1, because we want what? First output to be 0 and the second output to be 1. So for what values of input you will get this output, like that we can ask. So this query can be asked using ask vars. So this is the query. The query representation is something like this in first order logic, but you can ask it using ask vars. When you ask this using ask vars, it will return the possible output. So these are the possible output. These are the 3 possible outputs it can give: 1, 2, and 3. So I1, I1 can take 1, I2 1, and I3 0. This is one possible case for which the first output will be 0 and the second output is 1. The second possibility is I1 1, I2 0, and I3 0. Okay. The third possibility is I1 0, I2 1, and I3 1. For these 3 cases, the first output will be 0 and the second output will be 1. Right. Similarly, here is another query. What are the possible set of values for all the terminals for the adder circuit? That is what are the different possible values the circuit can produce? That is basically it can take 8 different inputs. So for each of the inputs, what is the different outputs? That is the question. So how can we represent that in a first order logic? So there exist I1, I2, I3. These are the inputs, and O1, O2. These are the output. Such a way that the first input to the circuit is I1, the second input to the circuit is I2, and the third input to the circuit is I3, right? And the first output is O1 and the second output is O2. So basically here we are asking the knowledge base to give everything. What are the I1, assign all the possible values for I1 and I2 and I3, and tell what will be the different outputs, right? So that's it about posing the queries. Debugging, sometimes when you post the query, if the answer is not correct, then we have to go back and check the knowledge base and we have to update the knowledge base. That process is called as debugging. Okay, so fine, let us stop here. Thank you.